Hello everyone. Today's video is based on as matter around USPO, Chapter 2, Class 9. Before starting this video, please like and subscribe to my channel LinkedIn Pharma. Let's start. Introduction. The concept of purity in the world around us delves into the nature of substances and their composition. Matter can exist as pure substances or mixtures, each with distinct properties and characteristics. Exploring whether matter is pure involves understanding elements, compounds, and the various ways in which they interact or combine. This brief introduction sets the stage for an exploration into the fascinating realm of matter's purity and its implications in our daily lives. What is a mixture? A mixture is a combination of two or more substances that are physically blended together, yet retain their individual properties. The components of a mixture can be separated through physical means, such as filtration, evaporation, or distillation, due to the fact that they do not chemically react with each other. Example. A classic example of a mixture is trail mix. In a trail mix, various ingredients like nuts, dried fruits, chocolate chips, and seeds are combined. Each component maintains its distinct taste, texture, and appearance, and they can be separated from each other without undergoing any chemical changes. This showcases the characteristic of mixtures where the substances involved maintain their own identities while coexisting in the same physical space. Types of mixtures. Mixtures can be classified into two main types based on the uniformity of their composition: homogeneous mixtures and heterogeneous mixtures. 1. Homogeneous mixtures. Also known as solutions, homogeneous mixtures have a uniform composition throughout, meaning that the components are evenly distributed at the molecular level. These mixtures appear visually consistent and do not show distinct boundaries between their components. Examples. Salt water. A mixture of salt and water where the salt particles are evenly distributed. Air. A blend of gases like nitrogen, oxygen, and trace elements that appear uniform at any given point. Activity for homogeneous mixture, solution, making saltwater solution. Materials needed: salt, water, glass or transparent container. Steps. Measure a specific quantity of water and pour it into the glass container. Gradually add salt to the water while stirring continuously. Keep adding salt and stirring until no more salt dissolves, and you see some salt collecting at the bottom of the container. Observe that the salt has dissolved and the solution appears uniform. Explanation. This activity demonstrates the creation of a homogeneous mixture, solution, where the salt particles are uniformly distributed throughout the water, creating a clear and consistent appearance. 2. Heterogeneous mixtures. Heterogeneous mixtures have uneven distribution of components, resulting in visible differences or separations between them. The individual substances in these mixtures can often be seen with the naked eye. Examples. Salad. A combination of various vegetables, each retaining its own texture and appearance. Trail mix. A blend of nuts, dried fruits, seeds, and other components that can be visually differentiated. Activity for heterogeneous mixture, creating a sand and water mixture. Materials needed: sand, water, glass or transparent container. Steps. Pour water into the glass container until it's about half full. Add a significant amount of sand to the container. Stir the mixture briefly and then let it sit undisturbed. Observe that the sand settles at the bottom, creating distinct layers in the container. Explanation. This activity illustrates a heterogeneous mixture where the sand particles settle at the bottom of the container, showcasing the uneven distribution of components. The layers formed in the mixture clearly demonstrate the separation of sand and water. Within these two main categories, mixtures can further be subcategorized based on their state: solid, liquid, gas, and the size of the particles involved. Mixtures can be as simple as a combination of two substances or complex with multiple components. What is a solution? A solution is a type of homogeneous mixture in which one substance, the solute, is dissolved in another substance, the solvent, at the molecular or ion level. Solutions are characterized by their uniform composition, meaning that the solute particles are evenly distributed throughout the solvent. Solutions can be formed with solids, liquids, or gases as solutes and solvents. Examples of solutions. 1. Saltwater solution. Solute, salt, sodium chloride. Solvent, water. Example, when you mix table salt, sodium chloride, into water, the salt dissolves and evenly disperses throughout the water. This forms a solution known as saltwater. 2. Sugar solution. Solute, sugar, sucrose. Solvent, water. Example, mixing sugar into water creates a sugar solution. The sugar molecules disperse and blend uniformly with the water molecules. 3. Air. Various gases, oxygen, nitrogen, carbon dioxide, form a solution in air. Example, oxygen and nitrogen are the main solutes dissolved in the gaseous solvent, which is air. 4. Brass. Solute, copper. Solvent, zinc. Example, brass is an alloy made by dissolving copper, solute, in molten zinc, solvent. The resulting mixture is a solid solution used in various applications, including musical instruments and decorative items. 5. Soda. Various solutes, flavorings, carbon dioxide, sweeteners, dissolved in water form the beverage. Example, carbon dioxide is dissolved in the liquid to create the characteristic fizziness of soda. 6. Alcohol in water. Solute, ethanol, alcohol. Solvent, water. Example, when ethanol is mixed with water, it forms an alcohol-water solution. This is commonly seen in alcoholic beverages like beer, wine, and spirits. Solutions have widespread applications in various industries and everyday life due to their ability to create uniform and stable mixtures. They play a crucial role in fields such as chemistry, medicine, food production, and more. Properties of a solution. Solutions, as homogeneous mixtures, exhibit several distinct properties that differentiate them from other types of mixtures. Here are some key properties of solutions. Homogeneity. Solutions are uniform in composition, meaning that the solute particles are evenly dispersed throughout the solvent. There are no visible boundaries or separations between the solute and solvent. Transparency. Many solutions are transparent, allowing light to pass through without scattering. This property contributes to their clear appearance. Particle size. The solute particles in a solution are usually very small, often at the molecular or ion level. These particles are small enough that they do not settle out of the mixture over time. Stability. Solutions are stable mixtures because the solute particles remain evenly distributed within the solvent. They don't spontaneously separate or settle over time, as long as the conditions are maintained. Concentration. Solutions can have different concentrations, which describe the amount of solute present in a given amount of solvent. Concentration is typically expressed as molarity, moles of solute per liter of solvent, or as a percentage. Physical state. Solutions can exist as solids, liquids, or gases, depending on the nature of the solute and solvent. For example, sugar dissolved in water creates a liquid solution, while air, a gas mixture, is also a type of solution. Colligative properties. Solutions exhibit colligative properties, which depend on the number of solute particles present rather than the nature of the solute. Examples include vapor pressure lowering, boiling point elevation, and freezing point depression. Electrical conductivity. Some solutions can conduct electricity due to the presence of ions in the solution. These solutions are called electrolytes, and their ability to conduct electricity depends on the concentration of ions. Color change. In some cases, the solute may impart color to the solution. For instance, food coloring dissolved in water results in a colored solution. Solubility. Solubility is the maximum amount of solute that can be dissolved in a given amount of solvent at a particular temperature. Different solutes have different solubilities in various solvents. Mixing efficacy. Solutions are easy to mix since the solute particles disperse uniformly throughout the solvent. This property is essential in various applications, such as chemical reactions and manufacturing processes. These properties make solutions versatile and widely used in fields ranging from chemistry and biology to industry and everyday life. They offer a way to create consistent and controlled mixtures for various purposes. Concentration of a solution. The concentration of a solution refers to the amount of solute present in a given amount of solvent or solution. It quantifies how much solute is dissolved in the solvent and is an important parameter in understanding the properties and behavior of solutions. Concentration is usually expressed using various units depending on the context of the solution and the concentration range. Here are some common ways to express concentration. Molarity. Molarity is defined as the number of moles of solute dissolved in 1 liter of solution. It is represented by the symbol m. For example, a 0.1 mole solution of sodium chloride means there are 0.1 moles of NaCl dissolved in every liter of the solution. Mass percent. Mass percent expresses the mass of the solute as a percentage of the total mass of the solution. It is often used in solutions where a solid solute is dissolved in a liquid solvent. Mole fraction. Mole fraction is the ratio of the moles of one component, solute, to the total moles of all components, solute and solvent, in the solution. It is dimensionless. Parts per million and parts per billion. These units express very dilute concentrations, especially in solutions where the solute is present in extremely small amounts compared to the solvent. Normality. N. Normality is used for solutions that contain species that can donate or accept multiple protons, H+ ions. It is defined as the number of equivalents of solute per liter of solution. These are just a few of the ways concentration can be expressed. The choice of concentration unit depends on the nature of the solution, the intended use, and the level of precision required. Accurate and consistent measurement of concentration is crucial in various scientific, industrial, and medical applications. There are various ways of expressing the concentration of a solution, but here we will learn only 3 methods. 1. Mass by mass percentage of a solution. 2. Mass by volume percentage of a solution. 3. Volume by volume percentage of a solution. Example. A solution contains 40 gram of common salt in 320 gram of water. Calculate the concentration in terms of mass by mass percentage of the solution. Solution. To calculate the mass by mass percentage, mass percent, of a solution, you need to determine the ratio of the mass of the solute, common salt, to the total mass of the solution, and then express it as a percentage. The formula for mass percent is: given data, mass of common salt, solute, equals 40 gram. Mass of water, solvent, equals 320 gram. Total mass of solution equals mass of solute plus mass of solvent. Total mass of solution equals 40 gram plus 320 gram equals 360 gram. Now, plug these values into the formula to calculate the mass by mass percentage. Mass percent equals 40 gram divided by 360 gram times 100%. Mass percent equals 1 divided by 9 times 100%. Mass percent approximately equals 11.11%. Therefore, the mass by mass percentage of the solution containing 40 gram of common salt in 320 gram of water is approximately 11.11%. What is a suspension? A suspension is a heterogeneous mixture in which solid particles or liquid droplets are dispersed in a liquid or gas medium. Unlike solutions where the solute particles are uniformly distributed and do not settle out, suspensions involve larger particles that are not dissolved and tend to settle over time when left undisturbed. Suspensions can often appear cloudy or opaque due to the scattering of light by the suspended particles. Examples of suspensions include muddy water. Water mixed with fine particles of soil or clay forms a suspension. The particles are visible and can settle at the bottom of the container. Orange juice with pulp. Commercially available orange juice often contains suspended pulp particles that settle over time. Paint. Paint is a mixture of pigments or solid particles suspended in a liquid medium. The pigments can settle, requiring thorough mixing before use. Blood. Blood contains red and white blood cells, as well as platelets, suspended in plasma. If left undisturbed, these components settle out, leading to the separation of blood into different layers. Chalk water. Mixing chalk powder in water creates a suspension where the chalk particles do not dissolve but instead remain dispersed. Suspensions have applications in various industries, such as pharmaceuticals, food, and cosmetics. However, they need constant agitation or stabilization agents to prevent settling, making them less stable than solutions. Properties of a suspension. Suspensions are heterogeneous mixtures that contain visible solid particles or liquid droplets dispersed within a liquid or gas medium. These particles are larger than those found in solutions and can settle out over time due to gravity. Here are some key properties of suspensions. Heterogeneity. Suspensions are visibly non-uniform, with distinguishable particles or droplets suspended in the medium. The distribution of particles is uneven, leading to variations in concentration. Particle size. Suspended particles are generally larger and can be seen with the naked eye. They can range from visible to microscopic sizes, depending on the suspension. Settling. Due to gravity, suspended particles tend to settle at the bottom of the container when the suspension is left undisturbed. This results in the formation of distinct layers. Tyndall effect. When a beam of light is passed through a suspension, the suspended particles scatter the light, making the path of the light beam visible. This scattering phenomenon is known as the Tyndall effect. Opacity or cloudiness. Suspensions often appear cloudy or opaque due to the presence of suspended particles that scatter light, preventing it from passing through the mixture. Stability. Suspensions are less stable than solutions. In the absence of continuous agitation or stabilizing agents, the suspended particles will settle, leading to a separation of the mixture into layers. Separation. Suspensions can be separated by filtration. Passing the mixture through a filter allows the larger particles to be trapped while the liquid or gas medium passes through. Mechanical properties. Suspensions can exhibit unique mechanical properties, such as thesotropy, where the viscosity of the suspension changes under stress. Some suspensions become more fluid when agitated and revert to a thicker state when left undisturbed. Examples of suspensions include muddy water, orange juice with pulp, and certain pharmaceutical suspensions. Due to their distinct properties and behavior, suspensions are used in various industries for applications such as medicine, food production, cosmetics, and manufacturing. However, their tendency to settle requires careful handling and the use of stabilizers to maintain uniformity in the mixture. What is a colloidal solution? A colloidal solution, also known as a colloid or colloidal suspension, is a type of heterogeneous mixture in which fine particles, usually solid, or droplets, usually liquid, are dispersed within a continuous medium, usually liquid, but can also be gas. Colloidal particles are intermediate in size between those found in true solutions and those found in suspensions. These particles are larger than individual molecules but smaller than what can be seen with the naked eye. Examples of colloidal solutions include milk. Milk is an example of a colloidal solution where fat globules, liquid, are dispersed in a watery medium. Mayonnaise. Mayonnaise is an emulsion of oil droplets, liquid, dispersed in water with the help of emulsifiers. Smoke. Smoke consists of small solid particles suspended in air. These particles are often colloidal in size. Ink. Ink is a colloidal solution where pigment particles, solid, are dispersed in a liquid solvent. Blood plasma. Blood plasma contains various colloidal components, such as proteins and other solutes, dispersed within a liquid medium. Colloidal solutions have applications in various fields, including chemistry, medicine, food, cosmetics, and materials science. Their unique properties make them useful for tasks such as stabilizing emulsions, creating specialized coatings, and delivering drugs in medicine. Properties of a colloid. Colloids, also known as colloidal solutions or colloidal suspensions, possess distinctive properties that set them apart from true solutions and suspensions. These properties arise from the intermediate particle size range of colloidal particles, which allows for their unique behavior and interactions. Here are some key properties of colloids. Particle size. Colloidal particles have sizes ranging from about 1 to 1000 nanometers. This size range places them between molecules in solutions and larger particles in suspensions. Heterogeneity. Colloids are heterogeneous mixtures, meaning that their composition is not uniform throughout. The dispersed particles are distributed unevenly within the continuous medium. Tyndall effect. When a beam of light is directed through a colloid, the dispersed particles scatter the light, making the path of the light beam visible. This phenomenon is known as the Tyndall effect and is used to distinguish colloids from true solutions. Stability. Colloids are relatively stable due to factors such as Brownian motion, the random movement of particles, and the presence of repulsive forces between particles. These forces hinder the particles from settling out or aggregating. Suspension. Despite their stability, colloids can eventually undergo coagulation or flocculation under certain conditions. Coagulation refers to the aggregation of colloidal particles into larger masses, while flocculation involves the formation of larger clumps that can settle. These processes can lead to separation and destabilization. Electrical properties. Many colloids carry an electric charge on their surfaces. This charge can arise from adsorbed ions or molecules. The electrical charges can result in electrostatic repulsion, helping to keep the particles dispersed and preventing coagulation. Brownian motion. The small size of colloidal particles allows them to be influenced by Brownian motion, which is the constant, random movement of particles due to collisions with molecules in the surrounding medium. Diffusion. Colloidal particles exhibit slower diffusion rates compared to molecules in a solution, but faster rates than larger suspended particles. Their intermediate size range contributes to this behavior. Interaction with external fields. Colloids can be affected by external fields like electric fields, magnetic fields, and gravitational fields due to their particle sizes and charges. Applications. Colloids have numerous practical applications, ranging from food and medicine, examples, drug delivery systems, to materials science, examples, colloidal coatings, and technology, examples, inkjet printing. Examples. Common examples of colloids include milk, ink, aerosols, suspended particles in air, and certain types of gels. Colloidal properties and behavior stem from the intricate interplay of particle size, surface characteristics, and interactions. Understanding these properties is essential for manipulating colloids for specific applications and maintaining their stability. Physical and chemical changes. Physical and chemical changes are two fundamental types of alterations that matter can undergo. They involve modifications to the properties and composition of substances. Let's explore the differences between these two types of changes. Physical changes. Physical changes involve alterations in the physical state or appearance of a substance without changing its chemical composition. In other words, the identity of the substance remains the same, even though there might be changes in its form, size, or state of matter. Physical changes are usually reversible and do not result in the formation of new substances. Examples of physical changes include melting of ice, solid water, ice, changes into liquid water. Boiling of water, liquid water changes into water vapor, steam. Crushing a piece of paper, the paper's form changes, but its chemical composition remains the same. Chemical changes, chemical reactions. Chemical changes, also known as chemical reactions, involve the transformation of one or more substances into new substances with different chemical compositions and properties. Chemical reactions often involve breaking and forming chemical bonds between atoms and molecules. They are typically irreversible and result in the creation of new substances with distinct properties. Examples of chemical changes include combustion, burning, of wood. Wood reacts with oxygen to produce carbon dioxide, water vapor, and ash. Rusting of iron. Iron reacts with oxygen and moisture to form iron oxide, rust. Digestion of food. Complex molecules in food are broken down into simpler molecules through chemical reactions in the digestive system. Key differences. Composition. Physical changes do not alter the chemical composition of substances, while chemical changes lead to the formation of new substances with different compositions. Reversibility. Physical changes are often reversible, while chemical changes are typically irreversible. Energy changes. Chemical changes usually involve energy changes, such as the release or absorption of heat, light, or sound. Physical changes may involve energy changes as well, but they are not necessarily tied to chemical reactions. State of matter. Physical changes can involve changes in the state of matter, solid, liquid, gas, while chemical changes may or may not involve changes in the state of matter. Indicators. Chemical changes are often indicated by the formation of new colors, the release of gases, the production of heat, and the formation of precipitates and soluble solids. Understanding the distinction between physical and chemical changes is crucial in fields like chemistry, materials science, and everyday observations. Recognizing the types of changes that occur helps us comprehend the behavior and transformations of matter in various situations. What are the types of pure substances? A pure substance is a type of matter with a consistent and definite composition, made up of only one type of atom or molecule. It possesses distinct physical and chemical properties and cannot be separated into simpler components by physical means alone. Pure substances include elements and compounds, both of which have consistent and fixed compositions. Pure substances are classified into two main types. 1. Elements and 2. Compounds. Elements. Pure substances compose of only one type of atom. They cannot be further broken down into simpler substances by chemical means. Elements can be categorized into three main groups: metals, non-metals, and metalloids, based on their physical and chemical properties. Here's a breakdown of these categories along with 10 properties associated with each. Metals. Metals are typically characterized by their shiny appearance, good conductance of heat and electricity, and ability to be shaped into various forms. They are usually solid at room temperature, except for mercury, and have a tendency to lose electrons in chemical reactions, forming positive ions, cation. Properties of metals. Shiny, lustrous appearance. Good conductors of heat and electricity. Malleable, can be easily hammered into thin sheets. Ductile, can be drawn into thin wires. High density and melting points. Often have a metallic luster. Tend to form cation by losing electrons. Solid state at room temperature, except mercury. High thermal conductivity. Form basic, alkaline, oxides when combined with oxygen. Non-metals. Non-metals exhibit a wide range of properties and are generally poor conductors of heat and electricity. They can exist in different states, solid, liquid, gas, at room temperature, and they often gain electrons in chemical reactions to form negative ions, anions. Properties of non-metals. Lack the metallic luster. Poor conductors of heat and electricity. Brittle, tend to break rather than deform under pressure. Often have low density and melting points. Variable states at room temperature, solid, liquid, gas. Tend to gain electrons to form anions. Can be good insulators. Often have low thermal conductivity. Form acidic oxides when combined with oxygen. Can be gases, like nitrogen, or brittle solids, like sulfur. Metalloids. Metalloids, also known as semi-metals, share properties of both metals and non-metals. They possess intermediate characteristics and can exhibit varying degrees of conductivity and reactivity. Properties of metalloids. Exhibit characteristics of both metals and non-metals. Often have properties that are intermediate between metals and non-metals. May be semiconductors, conducting electricity under certain conditions. Can be used in electronic devices due to their semiconducting behavior. Vary in appearance and physical properties. Examples: silicon, germanium, arsenic. The classification of elements into these categories helps us understand their general behavior and characteristics, guiding their applications in various fields, from materials science to electronics and chemistry. Compounds. Pure substances formed by the chemical combination of two or more elements in fixed proportions. They can be broken down into simpler substances, elements, through chemical reactions. Compounds are pure substances composed of two or more different elements chemically combined in fixed proportions. Unlike mixtures, compounds have distinct properties that are different from the properties of their individual constituent elements. When elements combine to form compounds, they do so in specific ratios, resulting in the formation of new substances with unique properties. Types of compounds. Ionic compounds. Ionic compounds are formed through the transfer of electrons from one element, usually a metal, to another element, usually a non-metal. This leads to the formation of positively charged ions, cations, and negatively charged ions, anions, which are held together by electrostatic attraction. Example: sodium chloride is an ionic compound formed by the combination of sodium and chloride ion. Covalent compounds. Covalent compounds are formed when atoms of different elements share electrons to achieve a stable electron configuration. These compounds typically involve non-metal elements. Example: water is a covalent compound formed by the sharing of electrons between hydrogen and oxygen atoms. Molecular compounds. Molecular compounds are a subset of covalent compounds where atoms are held together by covalent bonds. They consist of discrete molecules with a specific arrangement of atoms. Example: carbon dioxide is a molecular compound composed of carbon and oxygen atoms held together by covalent bonds. Organic compounds. Organic compounds are a type of molecular compound that primarily consist of carbon and hydrogen atoms, often with other elements like oxygen, nitrogen, sulfur, and more. Example: ethanol is an organic compound found in alcoholic beverages and used as a fuel and solvent. Inorganic compounds. Inorganic compounds encompass a wide range of compounds that do not fit the definition of organic compounds. They can include ionic compounds, covalent compounds, and more. Example: ammonium sulfate is an inorganic compound commonly used as a fertilizer. Compounds are crucial in understanding the behavior of matter and chemical reactions. Their distinct properties arise from the specific arrangement of atoms and the types of chemical bonds present within the molecules. The diverse array of compounds plays a pivotal role in fields like chemistry, biology, materials science, and many industrial applications. Difference between mixtures and compounds. Mixtures and compounds are both combinations of different substances, but they exhibit distinct characteristics and behaviors due to their underlying composition and the way their components interact. Here are the key differences between mixtures and compounds. 1. Composition. Mixtures. Mixtures are combinations of two or more substances where each retains its individual properties. The substances in a mixture are physically blended together and can be present in varying proportions. Compounds. Compounds are combinations of two or more elements that are chemically bonded together in fixed ratios. The resulting substance has unique properties that differ from the properties of its individual elements. 2. Separation. Mixtures. The components of a mixture can be separated using physical methods, such as filtration, distillation, or evaporation. The substances in a mixture do not undergo a chemical change when separated. Compounds. Compounds can only be separated into their constituent elements through chemical reactions. The separation involves breaking the chemical bonds between the elements, resulting in the formation of new substances. 3. Properties. Mixtures. The properties of a mixture are a combination of the properties of its individual components. Each substance in a mixture retains its own distinct properties. Compounds. Compounds have unique properties that are different from those of the elements that compose them. These properties arise from the specific arrangement of atoms and the types of chemical bonds present. 4. Formation. Mixtures. Mixtures are formed by physically mixing substances together. There is no chemical reaction involved in the process. Compounds. Compounds are formed through chemical reactions between elements. These reactions involve the rearrangement of atoms and the formation of new chemical bonds. 5. Examples. Mixtures. Examples of mixtures include air, a mixture of gases, salad, a mixture of various vegetables, and trail mix, a mixture of nuts and dried fruits. Compounds. Examples of compounds include water, formed by the chemical bonding of hydrogen and oxygen, carbon dioxide, formed by the chemical bonding of carbon and oxygen, and sodium chloride, formed by the chemical bonding of sodium and chlorine. 6. Reversibility. Mixtures. Most mixtures are easily reversible. The components of a mixture can be separated and brought back to their original state without any chemical changes occurring. Compounds. Compounds are generally not easily reversible. Once elements combine to form a compound through chemical reactions, it's often difficult or impossible to reverse the process and recover the original elements. 7. Energy changes. Mixtures. The formation of mixtures does not involve significant energy changes. Mixing substances together typically requires minimal energy input. Compounds. The formation of compounds involves energy changes, usually in the form of heat or light, as chemical bonds are broken and formed during the reaction. 8. Examples. Mixtures. Examples of mixtures include sand and water, milk, air, and various types of alloys. Compounds. Examples of compounds include water, carbon dioxide, methane, and table salt. 9. Variation in composition. Mixtures. The composition of a mixture can vary widely, as the relative amounts of its components can be adjusted. Compounds. The composition of a compound is fixed and constant. It is determined by the chemical formula of the compound, which specifies the types and ratios of elements present. 10. Chemical reactivity. Mixtures. The substances in a mixture retain their individual chemical reactivity. They do not react with each other on a molecular level, except in the case of reactions involving the mixture as a whole. Compounds. Compounds exhibit different chemical reactivity than their constituent elements. They react differently with other substances compared to how the individual elements would react. These additional differences further illustrate the distinctions between mixtures and compounds, highlighting their behaviors, properties, and the underlying mechanisms that govern their formation and separation. Thank you for watching.